So we're talking about work done by a constant force. Now, I think I forgot earlier to say it's work done by a constant force, because what if this force changed? It would be hard to know exactly what to do with it. We'll talk about that later. But anyway, we're talking about the work done by a constant force. And we know that the work is defined as F dot D. Dot is a scalar product. And the mathematics, all that means is F D cosine theta, where F is the magnitude of the force, D is the magnitude of displacement, and theta is the angle between the force vector and the displacement vector. Okay, so I had talked about what does negative work versus positive work mean, right? If we're talking about the work done by a force, sometimes W sub F versus W slash total, which is the work done by all the forces. Oh, since I just wrote that down, let's write down the work done by all the forces. The total work done is going to be the net force, right? So it's going to be the net force dotted with the displacement. That's the total work done. Let's think about that, right? Because or how do I know that's true? Maybe it's obvious, maybe it's not. But the work done by the total work done, let's say you have a bunch of forces, right? F1, F2, F3, right? They might be gravitational, tension, whatever, friction, F4, etc. on a body, just for example. Then the total work done is going to be the work done by the force 1 plus the work done by force 2 plus the work done by force 3 plus the work done by force 4, etc. Right? So the work done by force 1 is going to be F1 dot D, and the work done by force 2 is going to be F2 dot D, and the work done by force 3 is going to be F3 dot D. Whoops. Dot D. Work done by force 4 is F4 dot etc. etc. I didn't need to write out 4 forces. That's probably too many. But we can just factor out the forces, because the D and the D is constant, so it's going to be F1 plus F2 plus F3 plus F4 plus the rest, whatever other forces you have, dot D, which is just F net dot D. So we can differentiate between the total work done. Sometimes we call it the net work done, because we call the force the net force rather than the total force. But we, for whatever reason, we more often call it total. Total work done is F naught dot D. The work done by an individual force is that individual force dotted with D. I'd like to take that concept of the total work done one step further. I'm going to do what would be considered a proof, but it's a proof in one dimension that I'm going to then, rather than proving it generally, I'm just going to prove it in one dimension and then just say it applies even in 3 dimensions. And what I mean by that is, since we've got a dot product here, right, the net force on a body, let's say I have a body of mass M, a box of Cheerios, a cage with a rabbit, a car, whatever. It might be, let's put wheels on it, so I guess I've made it a car. It might be rolling down the road, so its displacement is in that direction. But we might exert a force on it in that direction. Now, that would be silly to do, but whatever. Maybe not. Maybe it won't be. Maybe we want to try to move it to the side, but we can't. But we're exerting a force in that direction. So F and D are in different directions. That's a 2-dimensional problem. And I guess... Yeah, sorry, I was thinking about doing this derivation in 2 dimensions, but I'm just going to do this derivation in 1 dimension. So that's a 2-dimensional problem. Let's keep it in 1 dimension. Instead of having my force possibly come at an angle, let's go ahead and just say, let's pretend that I exert a force in that direction. So then I don't have to worry about the dot product. The total work done is equal to the magnitude of the force times the magnitude of the displacement times the cosine of the angle between the force and the displacement vector. The force vector is going that way. The displacement vector is going that way. So the angle between them is 0. So it's going to be F D times the cosine of 0. And the cosine of 0 is 1. So the total work done is F times D. Oh, which F? What F is this? What F is this? This is the net force. And I was talking about sort of exerting a force, but it's the net force. That's what I had started with, the net force. So the net force, and we know that the net force on an object is m times a, so we get MAD. And we don't get mad, but we get MAD. Okay, so the total work done in one dimension is equal to MAD. Now I can make a substitution using kinematics, using constant acceleration kinematics. And here's something, again, I'm pulling something over on you here because I simplified this to one dimension. And now I'm going to simplify it to constant acceleration. But I'm going to tell you that the most important thing you could know about this derivation is that it holds more generally. It doesn't hold just for one dimension, and it doesn't hold just for constant acceleration. That it is going to be a very powerful result that we will use for the rest of the semester. Okay, so let's look at some kinematic relationships. So since it's one-dimensional, I'm not going to bother defining an x or a y-axis. I'm just going to say d was our displacement variable, so we can write it in terms of d instead of delta x or delta y. And I am putting a subscript f on v because v is always... So I had an alarm just to stop me, so I don't remember what I was saying, but I put the f on v. Right? V generally means v final, or v after a time t, and we don't usually put the f on it, but we put it on here just because to differentiate it from v initial, and you'll see why in a second. Okay, so let's go ahead and look. I've got an AD there and an AD there, so I'm going to make a substitution. Divide both sides by 2 of this last kinematic equation, so I have Vf squared over 2 equals V0 squared, V initial squared over 2 plus AD, and therefore MAD must equal M Vf squared over 2 minus VO squared over 2. And so therefore, ta-da, therefore, W total, the net work on any object, is always going to be equal to M, going to factor out the half that was in there, Vf squared over 2 minus V initial squared over 2, so it's 1/2 M Vf squared minus V initial squared, or 1/2 M V final squared minus 1/2 M V initial squared. Interesting. Okay, so the total work done, and then I'll say, as much as we use special cases, this is a general result. It is true always for any situation. The total work done on a mass or a system of masses is equal to 1/2 M times the mass, the total mass of the system, times the the final velocity of the system, which would be the center of mass of the system. It was more than one mass. Final velocity squared minus 1/2 M of the system times the initial velocity squared. We're talking about a single mass, so the system is a single mass. And because this is so important, we recognize that this quantity, 1/2 mv squared, is an energy, and we call it the kinetic energy. And I should write those words. We call it the kinetic energy. It's identified as the energy of motion, which is abbreviated KE, and KE is simply evaluated is the wrong word, defined as 1/2 mv squared. This is the energy of motion. When we talk about energy and we start to talk about energy and energy conservation, we'll see that there's two types of energy. There's energy due to motion, kinetic energy, or 1/2 mv squared, and there's energy due to position, which is potential energy, which has different forms depending on what kind of potential energy it is. But this energy of motion is super important. And you can see, therefore, if this is the final kinetic energy and this is the initial kinetic energy, then work total equals KE final minus KE initial, or simply the change in kinetic energy. Work total equals change in kinetic energy. This is one of the most important laws that you will ever learn in science. because it is really a statement of energy conservation, or it is the statement of energy conservation, and it is called the work-energy theorem. It is a statement of energy conservation that derives all other statements of energy conservation. So, for example, if you've already taken thermodynamics at some point and you know that the change in internal energy of a gas is equal to the work done plus the heat added, if you don't know that, then just ignore it. But that is really just a different statement of this work-energy theorem. We can ignore that statement, though, if you don't know what I'm talking about. So now you can see what I mean by work being positive or negative, speeding up a body or slowing down a body. If I had just a single force on a body, then the total work done is equal to the work done by that single force, and that's going to equal the change in kinetic energy of the body, right? So if the work done is positive, if W done by the force is greater than 0, therefore the change in kinetic energy is greater than 0, therefore 1/2 mv final squared minus 1/2 mv initial squared, or v0 squared, v initial, v sub 0, v sub I, it doesn't matter, but that is greater than 0, and so that tells us that therefore, because mass is constant, v final is bigger than v initial. Total work, if the work is positive, it speeds up. And the other way around, right? You can do it yourself, figure it out, that if the work done by a given force is less than 0, if that's the only force on a body, then V0 is going to be, whoops, I just wrote that backwards, then VF is less than V0. It means it slows down. Positive work means you speed up a body. Negative work, it means you slow down a body. Now, be careful. This is true for if there's a single force on a body, or that's true for the total force on the body. If the total work is greater than 0, the body speeds up. If the total work is less than 0, the body slows down. But it also means that, let's say that you have two forces doing work on a body. Two forces doing work on a body. Let's say that we have F1 pushing in that direction and F2 opposing it, pushing in that direction. Then if the body is going to move in one direction or the other, we're just going to have to guess. Let's just say, let's say we know that the body moves in this direction. Then F1 does positive work because it is trying to speed the body up in the direction of motion. F2 does negative work because it is indeed trying to slow down the body, right? So you can actually just talk about what is it trying to do, even though the body may be speeding up, or is, if F1 is bigger than F2, therefore the body is speeding up to the right, right? If F1 is bigger than F2, then the work done by F1 is greater than the work done by F2, and that means that the total work is positive. But what I'm trying to say is that whether a body actually speeds up or slows down, that has to do with the total work. But an individual force can be trying to speed it up, and another force can be trying to slow it down. So we know that if it was the only force and it was speeding it up, then the work must be greater than 0. If it was the only force and it was slowing it down, then the work must be less than 0. We'll do some examples soon to illustrate that. Yeah, let's do an example. Let's say that you've got your phone is sitting on a table. And let's say your cat, which cats do like to push things off, is exerting a force F. We'll call it even F cat. And there is a resistive force. Let's just give you some friction. There's a friction. Friction is a resistive force. And the cat is trying to push your phone off the table. So let's say that the force exerted by the cat is 7 newtons, and the resistive force, the frictional force, has a magnitude of 3 newtons. And ask, how fast is the phone going when it gets to the edge of the table? Oh, I guess I got to give you a distance. Let's say that it was sitting, I don't know, give us a distance. Let's say the phone was sitting 20 centimeters from the edge of the table. Okay, so and I want to know, how fast is the phone going when it gets to the edge of the table? Okay, so you could do this as a Newton's second law problem, we say we could draw a free body diagram, right? So F net equals ma. The net force is 4 newtons to the right. I'd have to know the mass of the phone. Whoops. So there we go. iPhone has a mass of about 120 grams. I know you may have something other than an iPhone, but it's all I could think of. Okay, so we could do net force equals ma, 4 newtons, mass 120 grams. Figure out the acceleration. Then use kinematics to go from the acceleration with the distance to a velocity. So we could use net force and kinematics in order to solve this problem. Absolutely. But we can also use the work energy theorem. Let's see how easy it is to use the work energy theorem, because the work energy theorem says that total work done is equal to the change in kinetic energy, 1/2 mv squared minus 1/2 mv initial squared. The total work done is the work done by the cat plus the work done by the friction, and that equals 1/2. And so then we just have to write the work done by the cat. The work done by the cat is equal to the force of the cat times the displacement, the magnitude of the force of the cat, 7 newtons, times the magnitude of the displacement, 0.2 meters, times the cosine of the angle between them. In that case, the angle between, look at the force of the cat and the displacement, the angle between them is 0, and so that is 1.4 newton meters, and the work done by the frictional force is equal to 3 newtons times 0.2 meters, magnitude of the force, magnitude of the distance, times the cosine of the angle between the frictional force, look at that arrow, and the displacement, look at that arrow. They're in opposite directions, so it's 180 degrees, and so that is minus 0.6 newton meters. Total work done, therefore, total work done is equal to 1.4 minus 0.6 newton meters, or joules, and that equals 1/2 times the mass, 0.12 kilograms, and we can just factor that out. V final squared minus V initial squared. What was V initial? Right, V initial wasn't stated, but it should be implied that it was 0 because the cat is pushing it, right? So the cat's pushing it from rest. Therefore, your phone's not just like floating on the table and moving all around on its own. So V initial is 0. So this is a single solution for a single variable. And we get 3.65 meters per second. The phone is going at 3.65 meters per second when it flies off the table. That's kind of fast, but that's okay. Kind of fast for a cat pushing a phone. I want you to notice a couple of things. First of all, we never had to we never had to choose directions because we have no vectors here. There are no vectors here, no vectors. This does not give us a vector, it gives us a magnitude of velocity because it's the square root of a quantity. So we don't have to worry about vectors. There were no vector components. If this was a 2 or 3 dimensional problem, there are still no vector components because this is not a vector equation. Makes our lives a lot easier. If we had done it with net force equals ma and kinematics, we would have had to use 2 separate concepts together, both of them paying attention to vectors. In this case, we don't. This is a lot easier way of solving this problem. Again, notice that because the cat speeds up the phone, the cat does positive work, but because the frictional force is trying to slow down the phone, it does negative work. Okay, so next time I'm going to do a couple more concepts that we need to know about work, and then we'll do some work energy problems to solve.